Good day, everyone. Welcome to our new webinar we've created together with some of our great members of the dental industry. We talk about together with manufacturers, but also end users. Today we have a really cool webinar, and that's called the next level in 3D printing and manufacturing. Let me take you through the agenda first. And there it is. I would love to introduce, one of the first things I want to do is do a panel introduction. I'm going to tell a little bit about 3D printing, but hey, who am I to tell you better than someone else who are most experienced in this field? We're going to have a presentation about why Asiga with manufacturing costs. We talk about composite tips and tricks. We're going to talk about approving materials, and approved materials, the reality of 3D printed hybrids, really from an end user, and the importance of post-processing. Now, as I told you before, I would love to introduce first our panel. Our first panel member is probably, we all know him very well. That's Graham Turner from Asiga. Graham, thank you very much for joining us and supporting us in this one. Graham is the Global Operations Manager from Asiga. The other panel member we have is an well-known digital dental technician, certified dental technician, and that's Lachlan Thompson. Lachlan Thompson is owner of Omni Dental Ceramics in Perth and in Melbourne. As I've introduced our panel, and we're gonna have great presentations from these guys, so please pay very careful attention because this is gonna help us all very much. I get one too far. I quickly want to say a little bit about why 3D printing. What is 3D printing? Why? It is the freedom to manufacture objects in a fraction of the time compared with traditional manufacturing processes. We're looking at ease, speed, reliability, efficiency. We all know traditional manufacturing processes like making a model by hand, by pouring a model in plaster, or milling an object in a milling machine. But sometimes we have to think about the processes we're currently doing. Are they the most smart processes we're doing? Can't we speed things up? Can't we make things more reliable, more efficient? One of the things is, especially working with equipment, is reliability of equipment. As we know, staff members, as much as we love them, as much as we love to talk with them, on Monday they're different production than on Wednesday or on Friday. And those things, when you are starting to utilize digital technology inside your laboratory or even your clinic, it is a little bit more predictable. Not even a little bit, it's much more predictable. So yeah, what we have to think about is smart production. One of the things we have to do is we have to think about what kind of objects are we want to make. We want to make models for crown and bridge work or for orthodontic treatments. Models, are we going to pour them? Are we going to mill them? That's even a possibility. Is that smart to do? Are we going to create temporary restorations, dentures, splints? All those things we have to think like, how can we make them and why do we make them in a certain way? Also, we have to think about object volume. If it's just one every week, it doesn't make sense. But do you have an entire room full of objects you have to put through in production? Yeah, what kind of system do you need? Do you need a big system? Do you need a small system? And that's why we're coming to the next point, and that is basically our equipment choice. Today we have a really beautiful webinar together with Asiga, and we're going to definitely talk about the Max UV and the Pro 4K 3D printers. And who am I to tell you all about it? I think I would love to give the word to Graham from Asiga, and he can tell you all about the Asiga 3D printers. Graham, I would love to give you at the moment the presentation. I would say blow them away. Thank you very much.
Thanks, Jerome. And thanks everyone for joining. I'll just bring up my my screen. Okay, can you see my screen's up there? Great. So I'm just going to run through a little bit about who Asiga is, and then just what makes our products different, and I'll give you a brief insight into how you operate our software to run the printer, and that's pretty much where you spend most of the time. Asiga is a 3D printer manufacturer primarily. We were founded in 2007 and we launched our first product in 2011. We're based in Sydney, and that's where all of our design and manufacturing happens for all our hardware, our printers. We do all of our own software development and our own material development as well. We've got an office in Germany that handles a lot of European tech support. And there are application specialists as well. So 3D printing, for those that are sort of new to 3D, the idea of 3D printing, it's basically a 3D printer is a system that will take your three-dimensional CAD model, it will slice that up into layers, and then it will print those layers one by one on top of each other until the object is fully formed or 3D printed. Now, the benefits of 3D printing in dentistry is that there are so many applications available. There are lots of materials now on the market for many different applications, and there are more coming. So we've got these images that are popping up. You've got surgical guide applications, which is pretty standard now, likewise for models. Newer materials on the market. There's been new advances in materials for splints, so there's some more flexible materials for occlusal splints. Denture bases is a big topic, so 3D printed dentures, which we'll touch on a little bit later. 3D printable teeth, and there are materials coming that are 3D printable for 3D printable aligners, and we'll expect to see some new releases over the next few months, I expect. Now, it can seem like a bit of a minefield when you start to look at the different options available, but there are some key factors that you need to consider when you're looking at a 3D printer for dentistry. Some of the number one is that you want to be able to produce parts accurately. If you can't produce parts accurately, then you will struggle to produce a suitable appliance, especially for a dental application. The next thing to consider is how repeatable or how reliable that 3D printer is, that technology. You want to make sure that you get good consistency from day to day, from week to week, from month to month. Speed's an important factor. There's some very fast 3D printers, there's some very slow 3D printers. The sooner you can get an object out of the printer, the better really for just reducing time to market, the potential of doing chairside. But we are also big advocates of open systems, so making sure that you have available to you the latest and greatest materials as they reach the market. And there are many material manufacturers now, with all that they do is focus on 3D printing materials. Some of the big leading brands that used to create analog or still do, they're now looking at 3D printable materials, so using their chemistry facilities and their chemists to develop new 3D printing resins. Now, why Asiga? Now, there are a number of reasons. The basic place to start is that our technology is based around DLP projectors, where a complete image or a complete build layer is exposed in one exposure, which makes them very fast. Now, a brief summary is that we've got a build platform that moves up and down into some liquid resin. The DLP projector is based underneath, so this is an upside down printer. and that projects images onto the liquid resin, polymerizing it or curing it, changing the state from liquid to solid, and it will keep curing every layer until the object is fully formed. DLP, the benefits are pretty clear. So you're exposing everything in one exposure, so one layer in one exposure. So they're very fast systems. Over time, they've got excellent X and Y stability. The pixels on the DLP chip in the projector, they don't move, they don't wander over time, they're fixed in place. So X and Y accuracy or stability over time is maintained. And we use UV LEDs, so an LED wavelength that is suited to some of the more technical materials available on the market today. Now, there are many other DLP 3D printers available. We always focus and always have done on the formation of every layer. So to make sure that the only way that you can guarantee that you'll produce a part accurately is whether you have some way of making sure that every formed layer is formed to the correct thickness. Now that's crucial to producing an accurate part. So we've got a series of technologies that we refer to as process monitoring technologies, where we monitor the whole layering process to ensure every layer is formed accurately and the result is an accurate print. Now, the number one technology is our smart positioning system, and this animation will just run through what that actually does. We basically detect the build platform position for every layer. So here these are the encoders here, the smart positioning system encoders. We've got a build platform that plunges into liquid resin, and underneath that we've got a DLP projector. As the platform plunges into the material, the sensors are activated. Now they're active as the material's flowing out of the way. The printer automatically just deflects as well because the liquid goo that it's plunging into just offers applies force back onto the platform. So we wait for the material to stop flowing before we send a signal to the projector to project the image. Then that means that the build platform is in the correct position before that image is exposed. So we get accurate layer thickness throughout an object. The next technology is that we've got an internal radiometer, then that monitors the LED power for the life of the product. So as the LED power reduces slightly over time, the curing times are automatically increased. We use high-powered UV LEDs, and the reason we use UV or 385 nanometers is because materials cure much faster at the deeper UV wavelength, so that you get much less X and Y light scattering, so you're able to achieve a much more accurate print. And you can produce water clear resins as well. So it's an invisible light, so you don't need pigments that are visible to us. So 385 nanometers allows us to print water clear resins. We use small pixels. We say for dentistry, for restorative dentistry especially, that the pixel size should be sub 65 microns. So all the products that we present to dental are under that. And we accommodate the materials compatible with our systems as really carefully. All materials behave very differently when they're being cured. So within our material curing profiles, we have a set of features that accommodate all the different behaviors, such as material shrinkage. You get offsets. And we basically, some materials are weaker or stronger than others as they're printing, so we accommodate all of that. So our end users have really good experiences with those materials. Now, on our new Pro 4K, we've got a 4K mode, which uses pixel shifting technology, which basically takes an image and reduces the pixel size by slightly shifting over the pixels. So in native mode on the Pro 4K 80, you can see there the resolution of the part. In 4K mode, that digitization on the surface just disappears. The pixel is reduced to 56 microns. Now, the ultimate is to get an accurate result. So when we were integrating with 3Shape Implant Studio, we found that over 93% of data points were within 50 microns of the original CAD data, with a standard deviation of around 31 microns. So that was a good feedback for us to really confirm that we were printing accurately. Now we're an open system, so Jerome's going to touch on some new materials from Ceramco and others, but we're open, so we work with most of the material manufacturers, the main ones in dentistry and other industries, to make sure that our customers have the correct curing profiles for when those materials are released, so you get seamless integration into your workflow. We develop our own materials. We've got a material for each application. And we've got a material library with over 400 validated material files now. They're available. As we expand that, all of those files are available to all of our users globally. We have two 3D printers really for dentistry. We've got a desktop compact Max UV, which is a very popular system. It's been on the market a few years now. It's very much a basis for all of our products now. And we've released the new Pro 4K, which contains all the same technology in the Max UV, but just bigger. It offers a build size 3 times larger than the Max UV. Key features is that we use a UV LED. On the Max UV, it's a 62 micron pixel. It's got a print speed of up to 60 millimeters an hour. That's material dependent. Some materials cure faster and allow for faster printing than others. And has a build size of 119 by 67 with a Z-axis of 76. Now, what that means from a performance or production output point of view, if you're printing models laying flat, you can get 2 to 3 models at 100 microns in about 20 minutes. Or for restorative, more accurate models, you'll print about a final layer thickness of 50 microns, and that takes a little bit longer, but it's still around 40 minutes. You have full control over what layer thickness that you want to print at. These are just presets that we have loaded in the software, but you can override them and print at whatever layer you wish. Standing, you can print 6 to 8 models in about 50 minutes. That's a full plate of denture bases on the Max. Now the 4K80, the Pro 4K80, it's a similar set of features, so 385 UV LED. It's got a 56 micron pixel when printing in 4K mode, which is a default printing mode that the machines are shipped with. Similar print speed to the Max, about 60 millimeters an hour, but with a much bigger build area. So we're printing at a 217 by 122 by 200 millimeters in the Z-axis. So this is a real volume system. So models laying flat, you're looking at anywhere from 9 to 11 models in about 20 minutes at 100 microns, or about 40 minutes at 50 microns. And then standing, it really comes down to how many you can get on that plate, like any application really, whether it's standing or laying flat. So you can get 20 to 26 models standing, and they'll print in about 50 minutes and 100 microns. Now, I've just got a summary of some of the costs. Now, I'll just give you the costs based on the material, and you allow for some wastage, which is basically in the supports that are applied to the parts to allow them to print. These are Australian dollars. So for dental models, say an average weight of 10 grams will cost you about $2.60. Surgical guides, they weigh less than dental models, so they're less, they're just under $2 a guide. These are, again, just the raw printed product. That's not with any finishing or with any sleeves in there. Denture bases comes down to material cost, but Jerome's going to talk about some new materials from Ceramco, from a Swiss company. To produce that particular denture base would be about 27 Aussie dollars. And for a full bridge, in their crown tech material, which is a permanent crown material, will cost just over $20. Now I'm just going to switch to Composer, which is our build generation software. Now this is the software which is the conduit really between your design program and an Asiga 3D printer. So to start, you basically click a new build and it will load the available printers to you. I'll just select one of our engineering systems. Now, because I've been playing around before this webinar, Ceramco is already pre-listed there. And you have, because we're an open system, you have access to our material library online. I could actually I'll just switch to that just to show you what that looks like. So in an Asiga account, an end user account, you get access to a bit more functionality than just without registering a product. Once you register a product, you get access to our material library, which looks a little like this. So basically, these are all the validated material curing profiles that we have available from each manufacturer. And given that we're talking about, we're going to go into Ceramco materials, to start using any of these materials, you basically go in and select the logo of the company that you'd like to use, and then you just download the curing profile. There are two materials that Jerome's going to show. Ceramco is already certified. There's a new material called dentures, which is coming, which will be certified soon. Before that reaches the market, there'll be a file in there. And inside these files are basically all the correct curing parameters for the material. You basically just download that file, and then you can load that into your Composer software. And then it will show up in you can dedicate a folder on your C drive or on your network for these third-party material files, and they'll just show up under this list. So you select Ceramco, and this is the available build area on the Max UV. So I'll just add in there a file, which is a full bridge that is part of some studies that Lachlan's been doing. He'll show you that later. Now that's been loaded, and it's not in an ideal position for 3D printing. So there are two ways really to print this. You can print this on an angle laying flat, rotate it around and laying flat, or print it on an angle. So if I'll just rotate this around. So I'll rotate that over. And then I can either basically just rotate this again to bring it flat, or I can bring it into an angle around 30 degrees. Either way, you can choose. You can find a format that works well for you. Now that's a purple color. It's just outside of the build platform. So I'll just use the auto place function here, and I'll just bring it into place. And then we just recommend you work from left to right across the top. So we've added the part. We can open up a build if we've got one saved. We can save the build here. We auto place the parts. The next icon along is generate support. So we just click on the supports. Now all of these settings here, they're all customizable. So you can change all of these, but all of these are preloaded in that file to offer best supports for that particular material. So we just click apply. And what these supports do, so that's the object supported. What these supports are doing is they're basically catching all of these, we call them islands. So the start of every tooth is an island. And it just needs to support the first layers to make sure that they are held in place. Otherwise, they'll float around in the build tray or in the resin. So using the auto support functions, just handy, it will collect all of those. Now, there are always some features in, or there can be anyway, you're dealing with quite complex geometry here. So it may pick up certain triangles that may be basically just showing up as needing support. To put a support point through here, now I know that I don't need that. I can just open up this dialog again and click remove, and then just click on the support, it will remove support. The reason we're printing it into orientation is to avoid placing supports on any of this fitting surface. So the fitting surface in here for the tie bar, I mean, is we basically don't want anything in there to obstruct the fit of that component. So we know that we can finish all of these surfaces down here, and the support points are designed to break away. So they'll break away really easily, and they will allow you to they'll leave a small bump where the support point was, and you can just remove them quite simply with a burr. So that's basically the object fully supported, and you can fill this whole area if you need to. You can print multiples if you want to as well, so you can just duplicate the part, or you can do an array where you can basically get as many in there as you want. So you can nest them, closely together. You can rotate them around and try and fit as many in there as you wish. But if you've got a number of cases, you can, that's where nesting becomes, important. And then you basically submit that to the printer. So you go to build, just to keep a log of what you're actually manufacturing. You can include the material batch, and that will allow you later on in this process just to export a build log to show what you've printed, when you printed it, the settings you used, the material that you used, and the batch of the material that was used. So you just go through the steps. All this is fairly simple and automated all the way through. We do have a new feature coming, which is called multi-range. I'll touch on that. We'll load a video on that separately, but that allows you to print different ranges in a build at different layer thicknesses. So you can print quickly through the supports and then slow down to areas that are required for fit. So you just basically then give it a build name. Here's the part map. Which I'll just switch the view. So here it shows the print of the material, all the build parameters that we used, the parts that were printed, the parts list, and I'll also give you a part map as well with all the parts numbered and labeled. So you can put that in your file for that particular build or that particular case, and then that's a good way to document your process. And then, yeah, you just submit the build to the printer. So you click send build. But I am connecting over a hotspot here, so it may take some time. What's important at the end of this is for those that may have some concern over the objects that you're printing. So you may feel that some area of the file may need some special attention. It will allow you to check the slices so you can make sure that the data being submitted to the printer looks right. So this just may take some time because I'm hotspotting to and across a network remotely. So I might just flick back to my presentation. That's basically that'll submit to the printer and it will show up on the printer menu, ready for printing. So from Asiga's point of view, all of our products are backed up by us. We offer unlimited lifetime tech support. That's included. There's no ongoing costs for that. And Asiga products are available through our reseller network globally. And that's me, guys. So I'll pass over to back to you, Jerome.
Thank you. Let me see. Yes. Thank you very much, Graham. I think very interesting to see definitely why Asiga is Asiga and why you guys are absolutely a game changer and different player in the dental, especially in the 3D printing industry. Also, thank you for you almost made a spoiler about the materials. I'm going into that one now. So all good, thank you. Now, like Graham also said before, is go into my presentation. We talk about approval of materials. There are so many materials available. We can go onto eBay. We can get all the materials, nice, perfectly fine. Are we able to use it? Basically, one answer: no. You have to be careful because we are making medical appliances that really go into patients' mouth, even if it's short term, long term, and everything. We have to be definitely sure it's safe to use. It's a responsibility of the manufacturer, but it's also a responsibility of the end user. Make sure that you check the data also yourself. Anybody can tell you a beautiful story, but check your own facts. I find it really important. So there are several organizations all over the world who check if materials are suitable in using usage for in the mouth. One of the organizations is the European CE approval. Most of the materials are basically anyway CE approved. Another one we have is the FDA approval. Based on that information of those institutes, we also have something else, and that is for our market here where the three of us are at the moment. It's the Australian TGA approval. And also something we have to realize an approval is not only pure on material. An approval can also be based on your workflow. It's saying, yeah, you can work with this material, but if you want to have the perfect end result to the point where it is approved, you need to follow certain steps. You need to have certain equipment that is allowed to work with it. We're going into it a little bit later. I know Lachlan tells also a little bit about how he works with things, and it definitely gives us a good story. Graham, like I said, you gave a little bit of spoiler. We're going to talk especially about Ceramco. Ceramco is a material that is really high aesthetic, and what we like about this material, it is a really good game changer in regards how we're going to do the production, because now the majority of our production is milling dentures, for example. Milling denture, yes, definitely it works, and in a lot of indications it can be a good situation. But is it a good situation for your milling machine only being occupied milling this material, or milling a denture PMA in a blank? Your milling machine is being used. Are there smarter ways how we can do production? And definitely we would say yes. One of the materials is the crown tech. Like Graham also said, this is a long-term material. They are in different colors available, and they are luckily TGA approved for us, so we are already able to use it. It is, we say, a glass infiltrated tooth print resin. It has really good aesthetics. It is really strong, a flexural strength of 130 MPa and the E modulus of 4000 MPa. This material is really suitable for denture teeth, for temporary crowns and bridges, but also permanent crown bridges. And you can even individualize this material. As Graham also told already, we are waiting for the approval of the denture tech material. And then we are able to print a full denture, hybrid, anything we want to use with teeth and gingiva material together. So then we have the full solution in basically your manufacturing. And Graham told a little bit about the printing cost. Yes, these materials are a little bit higher, but still average 27, 25 it was for the base. They're still very acceptable pricing. If you do a manual manufacturing, you have to do injection, you have all your manual work around it. It is much more time consuming, takes much more time. Thanks for not finding words. And also in your entire cost and your speed. I want to show one picture, and I am not gonna amaze you all because this is a picture I've done on my desk. But here you can see already the crown tech material. The tooth arch you see over here is made in A1 material, and the other ones are, I believe, an A2/ or an A3 even. But you can see a nice difference. But what I definitely wanted to show you in this picture is the translucency. Even though the material is, when it's thicker, it is more opaque, like natural tooth, and if you're going towards a thinner area, like the incisal area, you get a really nice natural translucency. It is a really good way in printing in one type of material, but getting different effects. We hope to have denture tech soon. We're really waiting for approval, so we're working really hard on that one, and we definitely will keep you updated. One of the other things is, at the moment, we're making splints, and I would definitely want to go into this one, for example. We also have a new material on the market that we currently deal with, and that is Keysprint Soft from Keystone. It is a really nice splint material because with that one you can print your flexible splints. What quicker, easier, and better way is it than print your splints? Traditional way is your injection or cold curing materials. Use that one, your acrylics, put it on, put it in a pressure pot, and well, most of us know that system anyway. Very time consuming, and it takes a lot of time. So this is definitely also a really good game changer in your production. What is very important, what we all trying to realize, especially in these difficult times, unfortunately we have the corona situation, COVID-19, that set us all a little bit back. We have to think smarter how we're going to do production. So we have to optimize our processes. And one of the processes is how to make everything in balance, your time, your cost, and everything. And if there is one guy that really understands how to do this trick, I have to point out to you, Lachlan, I give you a big applause for that one. You're really keen in how to utilize all your digital equipment and your digital knowledge in that one. And that is actually also where I directly want to stop here, give the presentation to you, and please amaze our dental friends what we are able to achieve nowadays already with digital technologies. Thank you for this one, and I'll give it up to you.
Thanks, man. Thanks for joining. I will get my screen going. Okay. So as Jerome said, I'm just going to pretty much go through what my experience has been in the lab with this these new materials that are coming out. I think, you know, we've always held out hope that there'd be some materials that can replace some real manually intensive work in the lab, and I think we're finally here with these two materials in particular. I'm sure there's going to be development, but the Ceramco material and the Keystone soft is pretty impressive stuff. Just make sure that support presentation. All right, so I guess, you know, this is ultimately my viewpoint from our lab and working in our environment. So I'm not going to assume that everything's going to be right for every individual, but definitely from our point of view, we've seen a lot of opportunity here with these two materials. Funnily enough, Graham, I saw that you posted something on Facebook, I think yesterday or Instagram maybe, about Asiga maybe 7 years ago with the Pico. I had a Pico, and that was the first 3D printer that I ever owned, and it was pretty much what I cut my teeth on. And so I thought, you know, the day before we do this presentation, it's amazing that these memories are coming back with this little metal printer that weighed probably 4 times what the UV does now. But it's amazing the progression, and amazing the progression of the materials and stuff. We were using it for a cast material then, and now with the library of materials that you guys work with, it's absolutely amazing to see. So I'm glad that we get a chance to look back in history sometimes and see where we come from, because it's changed so much in the dental industry especially. So congratulations on that one as well. So as I mentioned, I'm just gonna share some information with us with Keysplint and Ceramco. So with the Keysplint, it's a super interesting material. We have done and tested a lot of milled materials, and we haven't really found anything that really works so well. Sorry for the noise, guys. It's still within work hours, so there's work going on. The material is really interesting in a sense that at room temperature, the stuff is really hard. Like you would imagine it's similar to like a milled splint material. I'm just going to move some windows away. A milled splint material, and it's quite hard. So when I was doing a bit of research on the material, I came across a study. It's actually in the Keystone website that goes into the material properties, and the data is that as soon as it goes in the body at body temperature, the flexural modulus actually drops to 120 MPa from 1,100. So that blew my mind in the sense that, you know, if there's any type of discrepancy with the scan, which, you know, can happen depending on scan strategies, it's enough of the flexural modulus there to be able to pick up any sort of minor deviation on the scan. So the biggest thing for me with these milled splints, I mean, for us as a Crown and Bridge lab, we never ever went down the line of waxing splints. It just wasn't something that we were ever sort of involved in. As CAD/CAM sort of picked up and 3Shape had a splint designer software, we got more involved. So we started doing a lot of milling. But for us, if something didn't fit, it was pretty much a remake. And you're paying $120 or so for a disc, maybe 100 now at best. And if it didn't fit, you instantly, you know, you haven't made a profit. So what we found is with this material, as Graham sort of explained, you know, these printed parts are so cheap. So if something does happen to go wrong, it's not a huge deal to to be able to, you know, reprint it, or even print 2 at once, or if the scan's not right, reprint it, and the remake, you know, cost to the business is nowhere near as much. So I think why we would go down the line of printing splints is, as I mentioned, cost, you know, monetary cost. The time is so much more efficient that, you know, in terms of minutes being spent on these splints, and the capital investment. I mean, the other thing that we seem to forget while we're paying our leases, or, you know, however we finance our capital equipment, we're paying a huge amount for, you know, possibly a couple of hours to mill a splint, when that machine could be doing a lot more profitable work. So if we compare a, you know, max UV to a milling machine, obviously we have a lot more uses out of the machine than a mill, for a lot less money. I've just taken some screenshots out of this study. It's on the Keystone website, as I mentioned. This is a comparison between, you know, a few different materials, and some of the materials that we would utilize in the lab in the past. So this is a study that pretty much got a grinding machine and hit this splint material with a grinder, and then compared it to the other comparable options for materials on the market at the moment. So the standard one that we would have gone to, that I would have thought would be the best option out of all of these, would have been a, you know, clear PMMA disc, you know, dense PMMA. And, you know, they compare it with a key splint soft, and I've just taken those 2 out, so I've completely probably done the wrong thing by the study. But it's very interesting that we see here's a clear PMMA disc, and the depth of this abrasion is very deep, and there's a lot of deviation with the abrasion. It looks quite clean under the microscope, but the difference with the depth of wear, once this goes in the mouth of the key splint soft, is that the depth isn't that much, and the wear is more consistent. So I'm guessing that it's that modulus change that softens everything up, and it has this, it looks like it has a bit of a smear sort of wear characteristic over it. So this is a splint that I just designed yesterday on Splint Studio in 3Shape. The good thing about 3Shape now with Splint Studio, it probably takes about 10 minutes to design these, and very easy to make adjustments if you know, sort of have a look at it, print it, test it on the mold and go, oh no, that's not ideal. Make a quick design change, print it again, and then, you know, an hour and a half, you've got another one to polish up. The one on the right probably took about, the one on the right is obviously straight off the printer with the supports removed and clean. The one on the left probably took about 20 minutes, maybe 15 minutes to polish. So actually to get it to the point where it's highly polished and smooth, it's very quick. But the E-modulus thing really, or the flexural modulus really, I guess, got my attention. So I thought, why don't we just see what happens if we really abuse it? So this is a model, a splint that I'm about to put in boiling hot water. So straight, maybe not boiling, but straight out of the kettle. So thrown that in there, probably let it sit for about 10 seconds. You can see it. It almost turns to rubber. See, I've got, get a few calls about splints from clinicians, and they sort of want a material that if it's not fitting perfectly, they can just throw it in some hot water and stick it in the mouth, and it's still fit. So for me, this is like, okay, well, here we've got something that's really quick to make, quite cheap to produce, easy to polish. And if we want to sort of deform it a little bit to make it fit in the mouth, and the dentures can do that. So you can see it cools down and hardens. So I thought, okay, well, I'll throw it back in and see if it goes back to its original position. You can see it's moving back, so it's got some memory in the way that it's printed. So it pretty much moves back to exactly where it was before I put it in the water and deformed it the first time. So at this point, I've just let it cool down itself. And then I thought it'd be pretty interesting to throw that into a scanner and see where we end up in terms of accuracy from the print file to the splint. So this is the scan of the splint compared to the original STL. So there's always some deviation with these types of scans, especially when there's some clear, when it's a clear material. I've sprayed some scan powder on top of it. So you can see though, despite these areas that probably haven't scanned properly, the actual accuracy of the splint after throwing it into boiling water is absolutely insane. So you've got a memory there that if you want to heat it up, you can get it to fit. And if you want to pretty much reset it, you can throw it in some really, really hot water and it'll go back to where it was originally after it was printed. So I thought that was pretty interesting. So in terms of the other material, I'm going to go over the Ceramco stuff. So probably about 2 or 3 months ago, before all this stuff sort of went a bit sideways with COVID, we sort of got wind of this Ceramco material from Dental Access, and we thought, okay, all the studies look really good about this material. Maybe this is the one that we can actually get some final material or final restorations out of, and get some really nice, I guess, denture and hybrid options with this material. So for those that aren't familiar, our current situation to get a hybrid done, we use a very, very digital intensive workflow, but we scan the implant locations with an iCam 4D, take tissue records, merge those two together, and then we take our records into the 3Shape Denture Studio. We set up the order with a base with designed teeth, which is effectively taking the teeth and the base and separating them once it's designed. And we utilize, facial integration and stuff at this point as well, which is pretty cool. So once we've done a denture, a design, and got our teeth exactly where we want, we then bring that design and overlay it into the 3Shape bar design and get our bar exactly where we want it for our tooth position. So currently we're milling our teeth in a PMMA material. So you can see all the teeth are joined together, and that gets put into the CAM software and machine. So at the moment, a set of teeth like this, one arch, probably takes about, to get a high detail into proximal and occlusal milling, probably takes about 3.5 to 4 hours, depending on the size of it. So it's not the quickest thing in the world to machine, and if you're doing multiple cases at once, which we tend to do, you have 12 hours of milling, just teeth. So we'd mill the titanium in one of the machines and then mill the teeth in another. So obviously the capital investment just in that milling time alone is quite large. From there, what we do is as you saw with that, the 3D printed STL that Graham was demonstrating, we have a cutout of the teeth, which is the negative of the bar, and then we sit that over the top. And our thought process was, behind this was effectively making or keeping as much as we can joined together, so that we don't have as much of this tooth shearing. So upper and lower together, and then we go through and wax it. So this is the issue with us, like right now. We've got a digital process right up to the point where we're here, and then we have to throw a heap of wax on to encapsulate the whole lot, and then we inject it in the IVA base. So it goes completely digital. Everything's really nicely designed on the CAD software, and then we have to finish it by hand. I mean, it's still a hell of a lot more efficient than what it was, and the results are quite nice. But you know, we constantly have to sort of work out how we can become more efficient. So here comes, you know, the material that we've been talking about, is Ceramco print. So as Jerome mentioned, 130 MPa, which is, you know, really, really impressive for a print material. Most of them probably sit around 70, and a PMMA, like a standard PMMA, probably sits around, you know, similar amount. Obviously, they're probably slightly different wear characteristics, but that's about the ballpark of the strength. And so the way that I set up, effectively the same thing, right? Like same sequence in how we get to the point of manufacturing, but we're putting it on the printer at this point. So you can see I've decided to test this with the incisal edges up. In my mind, I'm thinking, okay, if I can not have to touch any of the incisal edges, I mean, I can get super artistic and put composite on it, but purely for this test, I thought, yep, let's do supports on the internals, the fitting surface. So that took about 1.5 to 2 hours. You can see actually one point here, the angle of the teeth is really, really important. If you have, what we found, if you have flat, a flat sort of angle on how you're setting your teeth up, some of them wouldn't print. And I think that's down to purely the support and maybe the separation force. I'm not exactly sure, but we found that we're getting, you know, now 100% print success with the angle of the setup of the teeth on the print bed on probably about, you know, 30-ish degrees. Then we do the same with the base material. So you can see here we've set this up in, you know, sort of like a hybrid type denture design. So this is the actual, I've got the actual print design, but it's, you know, that's pretty much it. Again, 1.5 to 2 hours. And then we've got the two parts together. So you can see there's a little bit of a white, I guess, reaction layer, maybe you'd say, on these teeth when they come out of the alcohol. And that just rubs off. It's a little bit strange the first time you print this material. You sort of wonder if there's been some kind of mistake with it, but that rubs off. And then if there's any areas that are difficult, you can just polish it off after. So stick the teeth and the base together, and then we go through and clean all the sprues up. And then what I've done is use the base resin, the pink resin, to join these two bits together. So you'll get it to a point, and the good thing about 3Shape is you have a lot of control over the settings between how the teeth fit and the base fit together. So you get it to the point where they lock in as they should, and then you can start flowing some of the pink resin material between the two and curing that. And that takes, you know, sort of anywhere between 30 minutes and half an hour. If you've got a titanium bar sitting in the middle, it's obviously a little bit more fiddly to do, but it's definitely not a super long process. And you can see what we've done with this one actually. We put a little bit of OptiGlaze stain, just a touch of white. So we've done nothing else but just stick a little bit of white on the incisal edges, just on the marginal ridges, just to see what sort of contrast we get. And it's funny, you know, like the one on the left, the photo on the left, we probably took, it would have been the end of day. We probably printed in the morning, took a photo at the end of the day, and the shade was meant to be A2. And you can see it's a little bit darker. Actually, no, maybe this is the day after. And then a week later, I've taken another photo, and it's gradually gotten lighter, and we worked out why. That it's down to the curing. So you have to really be sure with the post-processing that the curing machine that you're using is probably, I mean, ours is old, so it's probably about 2 or 3 years old now, so it's probably lost a little bit of that grunt that helps cure it. So if you cure it properly, then the shade ends up as it should. So after we stuck it to the bar, I took a couple of photos. Obviously, it's not the prettiest thing in the world because it's effectively just to see if the concept works. And the result's not bad. I mean, I haven't really cleaned it up so much around the teeth. I haven't done any staining or anything. It's just pretty much as it is. So this one, this one has no OptiGlaze. It's a different one from the other image. But you can still see that there's translucency. As soon as it gets to sort of a little bit thinner on the incisal edge, you get a reasonably nice translucency. I mean, let's all be honest. It's not as it would be if it was a multi-layered denture tube, but we're sort of we're in a different league at that point. And from my experience, there are some patients that absolutely love really intricate translucencies and stuff in denture teeth. Most of them, they hate it. They really don't care for it. So I think we've got a good sort of hedge here. We don't have a really opaque monocolor material. We've got some aesthetics here that we can work with. We can put some OptiGlaze on to develop that, and I mean, the result's quite good for really not a hell of a lot of work. So again, why do we want to print this material and print hybrids? It comes down to cost again, time, which is related to the cost, and again the capital expense is so much reduced because we're not having to use 2 milling machines. Even if we had 1 milling machine just milling titanium, and we wanted to do hybrid like this, then we'd definitely be better off and have the machine that's milling this PMMA, have it milling zirconia the whole time. So a couple of tips, because I'm sure some of you will get this in your hands, and I think there are some things that really alarm me. The post-processing is the key. There's no doubt about that. As I mentioned, the shades will lighten with time and curing. So you can see this image here is the day that I printed it. And I was getting in touch with Dental Access, and I said, this material, the shade's not right. It's a bit weird. And so it came out. It was more like a B3 shade. I mean, the Vivadent, SDL, DCL shade guide's not a classic, but it was still fairly close to like a B3, maybe A35 shade for an A2. And as you saw before, once it had sort of sat for a day even, it really lightened up, and then a week it was like bang on A2. So it sort of alerted us that we need to look at our post-processing, and that's something that you will all need to sort of make sure you've got covered. The other thing is that you don't want to, when you're joining these two things together, the teeth and the base, you don't want to put a heap of resin in and cure it. You want to do sort of small amounts at a time, because what will happen is that you have uncured resin in the center of these masses, which we found out when we did our first test with the bar. What happens is, and you'll see in the next video, is that some of the material doesn't cure around the bar, and then that's of course where you'll get really bad delaminations. But other than that, super easy material to handle, and the aesthetics are really good. So the last video is pretty much as dental technicians like to do, is destroy things if we're testing. So this was, I guess, our comparison to what we're doing with PMMA, and it's pretty impressive in the abuse that it takes. excuse the mess. It's obviously probably middle of the week. So this was an air chisel, straight on the centrals. It had a tiny little fracture there, which I think was there before. So I'm pushing really hard at this point. Straight over the screw hole, trying to get something to pop. So I've never seen a printed material do something like this and behave like this. It was pretty impressive. So now I thought, okay, well, I'll go straight over the screw holes and see if I can sort of lever at the back of a screw hole. Then we had a little chip on the central. So you can imagine the force in the mouth that it'd take to have to get this, break it like that. It's a fair chunk of force. The next one is, I was pretty impressed at that. I thought I'd take it another step further. Just get forward a little bit. Sorry, that's a replay. So we have to bring out the mallet to give it a real test. So I stuck it against the bar over our bin. Just started hammering it. So I had tiny delamination off the premolar there. And then just went to town with it. So like anything, it will eventually crack and break. But that's the point where I realized that there's uncured resin in there between the bars. So we'd, taken it back to the bench and started, having a good look at it. And there's been resin in there that I've lumped too much in, and it hasn't cured around the bar. So I'd imagine that the next one that we'll do, which probably be next week, we'll just do a little bit less material at a time and cure that, and then treat the surface again, cure again, cure again. It'll probably take 3 cures to get it to the same point, but I'd imagine that strength will be improved greatly from that. So my sort of take on this stuff is that ultimately both materials are huge time savers, which is what, now that I guess things are going digital and we don't have as many trained people, time is key for us. So really cutting down that is what we sort of, I think for us anyway as a business, have to really sort of focus towards. Splint manufacturing with 3D printing is finally reality. There's been other materials out there, and I'm sure there'll be some that are similar, but this soft splint's one that I've found that is probably it. Like I think that the flexural sort of characteristics of it are amazing, and that it's really quite economical to manufacture. The denture materials are actually now on par or better than traditional materials. So we're always sort of having these materials that were promised to replace denture, traditional dentures, and I think the materials were always a little bit softer, a little bit weak. You do a test and it would break straight away, and the aesthetics were always probably a compromise compared to a traditional denture tooth. Where I don't think this is. I think this is a really, really nice material. In terms of fixed, I think time will tell how that goes. Replacing the materials, the acrylic materials on a bar. I think we just have to see how it goes. We'll run some tests and report back. But I think at the very least, this material is perfect for removable dentures. It's going to provide as good a strength and wear characteristics as a standard denture material, and be really efficient to produce. So you know, I think for me it's a slam dunk. So yeah, look, I think you get your hands on it and have a play with it and see how you can sort of get it to fit into your workflows. As with anything new, there's probably a few questions that I haven't answered here. So if you need any more information on it, feel free to reach out and send me an email, and I'll get back to you as quickly as I can with that, and hopefully it all works out.
Thank you, Lachlan. Really, really beautiful to see, and the digital possibilities, what we all can do. Really, thank you for that. Let me put the presentation back to my side. It is really good to see the entire workflow that you're doing, your tips and tricks. We can definitely see a change if we're going to do production. And one of the things is you mentioned your post-processing. I want to talk a little bit later about that one. I want to first talk to you a little bit about common sense and PPE. A lot of people might laugh about this one, but it is something definitely we have to think about. And I hope everybody is able to see my screen at the moment. We've came across a lot of, since we're in the digital industry and doing 3D printing, we came a lot of weird things especially in the beginning of the first print years. And now people come up with skin reaction even materials, because in the beginning of 3D printing, there was not much known about the chemicals that was used, and people were like, yeah, it's okay. We all ignitions. We put a little bit of monomer on our fingers, we put it in our mouth, and we continue. I think it is a well-known case how we work. So that's, again, I want to reach out, say a little bit common sense and PPE. One of the things is use on a stable surface and table. It's not so much for spoilage, but also my print or my scan is not so accurate. Yeah, why? Because your equipment is on a table that's unstable. It moves, someone walks by, it moves. You get a little bit of inaccuracy. We want to have a clean and a surface that's easy to clean. So, for example, when you have a stainless steel plate underneath, you can easily wipe it off, put some IPA on it, and done. One of the very important things is work in a well-ventilated area. I started printing about in 2005. I started with small things, just testing, and in the years later, also I had a printer next to me, and at a certain point, I'm like, yeah, I still have some headaches at the end of the day. One of the reasons is, yeah, of course, you're sitting next to a chemical that is being light cured. There is a different process coming on. Fumes are coming off. To make sure you print in a well-ventilated area. Also, don't put your printer in a direct sunlight. These materials are UV light curing materials, so be aware. Also, especially the material from Ceramco is really light sensitive, so even be with that one very carefully. Safety goggles, I don't have to tell. Preferable use nitrile hand gloves, no latex. It's seen that some materials have a chemical reaction with latex, and we, as we sometimes dress up, if we have something on the lab side, just use a lab coat. Protect your own clothes, protect the clothes from the people around you. Like I said, some people might laugh about it, but I think we have to point that one out. The other thing is that Lachlan also mentioned is about there it is, about post-processing. Post-processing is one of the more important tasks after 3D printing, because you can have the best, most beautiful printer. You can spend a lot of time, you have an entire row, you've invested in an entire print street. If you don't do your post-processing correctly, the print has failed anyway. because what comes out of the machine is not 100% finished where you want to be. So think about that one. Invest in good post-processing process. Not only for that to get a good end result, but it's also for some materials obligated. And like I talked previously about the TGA approval, you need to have the right products in line. So what we're going to do when we have printed an object is we're going to say we're going to clean it. We're going to clean the printed object with some IPA or a mixture in the wash unit. You see on the left top corner, you see a formula wash unit. It's a simple unit, works well. Or you can use an ultrasonic bath, for example. There are multiple ways to do it. Then we need to have a light curing box and especially when we are printing with biocompatible materials, the 385 is very important. The light curing box that Asiga provides is a really good box for basically all of the materials, but except when we talk about the Ceramco crown pack and hopefully soon the dent pack material and the key splint. So there they are saying with the approval of the TGA, you need to post-processing light cure it in a good light curing unit. And in this case, we'll talk about the MK Optic Auto Flash. For Ceramco, you'll need the Auto Flash with a nitrogen gas. For the key splint, you don't need the nitrogen gas option, but it is still both. You need this machine. It is always very good to invest in that one. So like I said, always post-process for a final result. One of the things that we talked about costs. As we all know, we're going at it's the end of financial year. We are all very good in making the most beautiful deals and help you out. Thank you, Lachlan, for sharing your email address for if anyone has a question. But I want to reach out to you guys. Now, it's still end of financial year here in Australia. And if you really want to benefit now of really good deals, please reach out to us. Not only that is we have the 150k per asset tax write-off. And they've extended it a little bit longer, but the benefits, the deals are being made now. If you want to still benefit of that, please reach out to us and we see where we can help you best, where we can look into your unique manufacturing process and we can say this option might be best for you. There is not always one solution. Now, like I said previously, for milling zirconia, yes, we don't do that on a printer, so we use a milling machine. Lachlan said also, like, yeah, does it make sense to mill all my PMA star material on a milling machine while I can have it more effective when it mills my zirconia? So think about that. We always have a solution for you guys. If there are any more questions, I would definitely love to ask you to reach out to us. You can send an email to info@dentalaccess.com or follow us on social media and contact us by that. Here, please follow our social media channels, not only for me, but also, of course, for my panel members that have joined me today and were really, yeah, how do I say it best? I don't even know what I'm saying. My gratitude is very big, and I would love to thank you guys for telling your story, telling your experience, and making this beautiful webinar happening. Follow them also. It's always good to see what other people are doing. And
thank you.
Gives me the last slide. It is all, we're not alone, we're all working in teams, we all have each other's back, and especially in these challenging times, we need to do that. So for me, I've got nothing else to say. Then please stay safe, and if you have any questions, reach out to any one of us and we'll help you wherever we can. Have a great day. Thank you very much. Bye-bye.